Hello, bonjour. Sein bei nous, c'est le métis B. Welcome to the 10th week of Statistical Mechanics, Algorithms and Computations from the Physics Department of École Normale Supérieure. This week's lecture is devoted to a discussion of the alpha and the omega of Monte Carlo. The alpha will be Count Buffon's legendary needle-throwing experiment that has fascinated many people, children and adults, learned circles and noble courts ever since its invention in 1777. It will lead us to a discussion of variance reduction methods. The omega will be Levy's stable distributions that anybody interested in statistics and especially in Monte Carlo algorithms has to be at least aware of. It will lead us to a discussion of the case when the variance of an observable is infinite. So this week's tutorial will contain a short review of all the material covered during these 10 weeks, and then we'll have a party. So let's get started right away with this week of Statistical Mechanics, Algorithms and Computations. The experiment consists in randomly throwing needles of length A onto a wooden floor with cracks that are a distance B apart, like this, like this. The positions of the needles are random on an infinite floor. The needles do not roll into cracks as they do in real life. They do not interact with each other. And the angle phi is randomly distributed between 0 and 2 pi. So let us introduce variables x and y. Clearly y is irrelevant to the problem, and r center and phi. All the cracks in the floor are equivalent, and there's a symmetry between the tip and the ear of the needle, and there's also symmetry between phi and minus phi. So we may look at a reduced problem where phi goes from 0 to pi over 2, that means to 90 degrees, and x center goes from 0 to b over 2. We suppose that the angle phi is uniformly distributed and also that x center is uniformly distributed. Now, the x variable of the tip is given by x center minus a over 2 times cosine of phi. And if x of the tip is smaller than 0, we have a hit. More precisely, the number of hits of a needle centered at x and oriented along phi is given by n hits of x and phi, which is given by this formula. And the average that we want to compute is given by the integral, as we had many times in this course, the integral over x from 0 to b over 2, the integral over phi from 0 to pi over 2 times n hits of x and phi, divided by the normalizing integral dx from 0 to b over 2, d phi from 0 to pi over 2. This gives the following integral. So we have the solution of our problem under the condition that we know how to integrate dx from 0 to 1 of arcus cosine x. Well, think about it twice and you will find out that it would have been wiser to first integrate over x and then integrate over phi. And we find that the expected number of hits is proportional over an integral d phi from 0 to pi over 2 times cosine of phi, and this integral, we know how to do it, it is equal to 1. So we end up with the result that the expected number of hits is a over b times 2 over pi. So in the special case, when the length of the needle a is equal to the distance between the floorboards, we find that the number of hits is equal to 2 over pi. So by throwing needles onto a parquet, we can compute the number pi. This is what has fascinated many people since 1777. We can now write a program to do the Buffon experiment ourselves. It suffices to sample x between 0 and b over 2 and phi between 0 and pi over 2, and then it is necessary simply to check where the tip of the needle is on the other side of the crack as shown here. Well, you see that in this program we have pi input because we have a random number between 0 and pi over 2, and this program is supposed to compute pi, so you might be interested in a historically authentic version that does the Buffon experiment without inputting pi. This is shown here in the patch. So now we can do Buffon's experiment for as many needles as we want to. And you see here the output for 2,000 needles being thrown on the parquet. Let's look at this program, the output. And let's ask a question. How do the needles hit the cracks? Do they hit the cracks more at the tip, at the ear, or at the center? Can you tell from this picture? So we want to know whether the needles hit the cracks more at the tip, the center, or the ear. Mathematically speaking, we can introduce an internal variable L that goes from 0 to A, and n hits can be written as an integral over L from 0 to A of n hits of L. Now we can go into a mathematical argument and a probabilistic reasoning. But it is much easier to look at this question experimentally. So now, in order to find out whether we have more hits at the ear, the center, or at the tip, and in order to avoid getting into probabilistic arguments, let's take a second needle here, and let's make a little gadget. This will be gadget number 1. Okay, just a moment. All right, you see that the center coordinate of one of the needles is equal to the ear coordinate of the other. Now see the gadget 1. I throw one of the needles randomly onto the floor. But if I don't tell you which one of the needles was thrown randomly, you will not be able to tell. You see that the number of hits at the tip of one of the needles must be equal to the number of hits at the center of the other needle. But because these needles are equivalent, we have proven, more or less, that the probability or the mean number of hits at the center must be equal to the mean number of hits at the tip. Now we could glue together the needles at different parts of, we could glue them together like this, or like this, or like this. And we prove like this that the hitting probability, n hits of L, must be independent of L. And by this, we can prove that n hits is equal to a constant times the length of the needle. So the gadget that we had before was length 3/2, has 3/2 as many hits as the original needle. And this we already saw in our starting calculation, because the number of hits was proportional to A, the length of the needle. So now, can we compute upsilon without doing a complicated calculation and computing the integral of arcus cosine x? And indeed we can, because the world of gadgets is not limited to straight gadgets. We can glue together the two needles like this at an angle. So let me do this. Look here. All right. So this is my gadget number 2. It is a needle, a bent needle, that also has an internal variable that goes L, that goes to L from 0 to the length of the needle, and I can throw this gadget. Now look at this bent needles gadget number 2 that I throw onto the floor. Each point along the interior variable collects hits as if it was by itself. So what I will find is that each internal point on this gadget has the same mean number of hits as it was before. And this remains true even if the needle itself was not just the joint of two straight needles, but even if it was a curved needle. So we find the very strong generalization that the mean number of hits is equal to upsilon times the length of the needle, independent of the shape of the needle. So now this has a very strong consequence that was first found out by Barbier in 1860. He considered throwing needles of length pi times b. So let's start with straight needles. And let's do this experiment here on the screen. So here I throw first needle, second needle, third needle, fourth needle, and so on. You see that the number of hits can be equal to 0, 1, 2, 3, or even 4. Now we can do the same experiment with needles of length pi, but of different shape. We can take round needles and of length pi, and let's throw them. First, second, third, fourth, and so on. So what Barbier first noticed is that for the round needles we have 2 hits, 2 hits, 2 hits, and 2 hits. But for the round needles we also have the law that the mean number of hits, which is equal to 2, is equal to epsilon times the length of the needle. But this length of the needle is pi. So we find that epsilon must be equal to 2 over pi. And you see that Barbier was able to compute for us the outcome of the original needle experiment without ever doing this experiment. He found without any calculation that n hits must be equals to 2 over pi times a over b, and that is the final result. But now, wait a minute. We find that the outcome of the round needle experiment is the same as the outcome of the straight needle experiment? No, of course not. Let us look at the 2 experiments, the straight needle experiment and the round needle experiment, on their respective landing pads. So for the straight needle experiment, as a function of x and phi, we see that we can have 0 hits, 1 hit, 2 hits, 3 hits, and 4 hits. And we find out that the mean number of hits is equal to 2. This would be quite a complicated calculation if we did it ourselves. And it would be quite a complicated Monte Carlo simulation because we would have a lot of fluctuations. Now let's look at the landing pad of the round needle experiment. Again, we have the variables x and phi, and the number of hits is 2 everywhere. We have no fluctuations, and the outcome also is 2. But the 2 experiments are of course different. It is only the observable, the mean number of hits, which is the same. So if we are only interested in computing the mean number of hits, we are much better off in changing our experimental setup and doing the round needles than the straight needles. What I explain here in a very simple setting, but a very famous setting of the Buffon-Barbier needle experiment, has many applications. And it is called variance reduction. Because you see here in the round needle landing pad, we have complete variance reduction. The variance is equal to 0 of this observable. And in the other, the variance is very large. So this variance reduction is a powerful concept. It means that we will redo a new calculation and think about a new setup of our algorithm for any observable that we want to compute. So before continuing, please take a moment to download, run and modify the 2 programs that we discussed in this section. There is directneedle.py that does the original experiment, and directneedlepatch.py that uses inspiration from the Monaco games to avoid computing sines and cosines and using the input of pi to compute pi. And especially try to really to think over this amazing argument by Barbier telling us that the mean number of hits is proportional to the length of the needle independent of its shape. This is called Barbier's theorem. All during this course, we have insisted on the relationship between sampling and integration. So, to wrap it up, for the omega of Monte Carlo, let's do one last integral. We call it the gamma integral, integral from 0 to 1 x to the gamma. This very simple integral can be done analytically. The outcome is 1 over gamma plus 1, and this integral exists for gamma larger than minus 1. So let's do this integral by sampling. Simply take x as a random number between 0 and 1 and compute this random number to the power of gamma. This is done in the program directgamma.py. And we are adding a few lines to do the error analysis. We compute the mean value, we compute the mean square value, and afterwards we output the value of the gamma integral plus minus the error. You notice that here we have a direct sampling algorithm, not a Markov chain sampling algorithm, so that the Gaussian error analysis is okay. So output of this program directgamma.py is shown here for gamma equals to 2, 1, 0, minus 0.2, minus 0.4, minus 0.8. You see that most of the time the outcome of the integral plus or minus the error agrees with the analytical result. But for gamma equals to minus 0.8, where the program runs just fine, we get the result that the gamma integral is equal to 4 approximately plus or minus 0, 1. But this does not agree with the analytical result, which would be the gamma integral is equal to 1 over gamma plus 1, so it is 1 over 1 minus 0.8 is 1 over 0.2, which is equal to 5. To make progress, let us modify our original program directgamma.py and compute the running averages. So for all during a very long simulation, we output what would be the current estimate of the gamma integral by computing the sum of the observables, the random number to the power of gamma, divided by the length of the run. So this gives direct gamma running.py. Output of direct gamma running.py is shown here. You see initially we have very unpredictable result, and then for a very long time the simulation zeroes in on a result which is different from 5, the exact value. And then after hundreds of thousands of trials, all of a sudden we hit an enormous value of x to the gamma. Notice that gamma is negative, so if x is close to 0, the value becomes very large. So here we see that we approach a wrong result, and all of a sudden we go through the roof and we continue our calculation. So clearly, because the running average is constant, we also have an error estimate, the average over the x to the power of 2 gamma, which comes out much too small. Then the very large sample hikes up the mean value and also increases the error estimate. Now let us analyze what is the problem here. The problem is that we have an estimation of the variance of our distribution as the sum over the random numbers to the power of 2 gamma, as you see here in the program. And this sum approximates an integral, which is the integral from 0 to 1 dx x to 2 gamma. So this is integral from 0 to 1 dx x to the minus 1.6, and this integral is infinite. So the distribution for gamma equals to minus 0.8 exists. It is finite, but it has an infinite variance. Clearly, the situation is very difficult to analyze in the absence of an analytical solution. Now we continue in 2 steps to analyze the gamma integral. What we will do in a first program, Dirac gamma average.pi, is we take the average, sigma divided by n, and we compute the probability distribution of sigma over n as a function of the length of the interval over which we average. We take n equals to 1, 10, 100, 1,000, 10,000, and 100,000. For n equals to 1, we have the original integral, and its probability distribution is given by pi of sigma over n is equal to sigma over n to the power 1 over sigma to the n to the power of minus 1 minus 1 over gamma, as we discussed previously in lecture 4. So it goes like this, and it decreases like x to the 1 over x to the power of 2.25. Then we take the sum sigma over n for n equals to 10. We get this distribution. Then for 100, we get a new distribution, for 1,000, and so on. All the averages are equal to 5, but the most probable values only very slowly approach 5. And this was the reason why we obtained a wrong result, because the average turned out to be very different from 5. So finally, let me give you, without justification, a way to rescale all these curves onto one universal curve. So this rescaling is the following. Instead of considering the probability distribution of sigma over n, we consider sigma over n minus the mean value divided by n to the minus 1 minus gamma. In our case, gamma is equal to minus 0.8 and the mean value is equal to 5. So we have to look at the histogram of the mean value sigma over n minus 5 divided by n to the minus 0.2. And you see that the same data that depended so much on n falls onto the same curve, approximately for large n. This is shown, is written up in the program Dirac gamma average rescale.pi, which also contains the analytically known limiting distribution in the limit n going to infinity. This distribution that you see approaching here for n larger and larger, and that you see written here as the analytical formula, is one of the examples of the famous Levy stable distributions. These Levy stable distributions depend on the power gamma of our distribution that has infinite variance, and on the precise asymptotic behavior for x going to plus infinity and x going to minus infinity. So in our case, the distribution for x going to plus infinity is 1.25 divided by x to the power of 2.25, and it is 0 for x going to minus infinity. And what Levy showed in the 1930s is that these very erratic distributions, as we saw in our initial calculations, satisfy very strict laws and obey in the limit n going to infinity. If they are properly rescaled, they obey these stable Levy distributions. So before concluding this lecture and this whole lecture series, please take a moment to download, run and modify the programs we discussed in this section. There was direct gamma.pi, the program that was supposed to compute the integral dx x to the gamma between 0 and 1, and that had a lot of problems doing this for gamma between minus 1 and minus 0.5, even though the integral existed. Then there was direct gamma running.pi, the program that computed the running average and had these points going through the roof. Then we had the program direct gamma average.pi and direct gamma average rescale.pi. So in conclusion, we have studied in this lecture two outstanding problems, the original Buffon needles and the famous Levy stable distributions that brought order and understanding to very erratic random processes. So let me thank you for all of your interest and the very active participation during this course.